Okay, the idea behind kinetic molecular theory is that a lot of the properties of solids and liquids, and especially gases, can be explained not so much by the chemical properties of the atoms and molecules, but by the way they move. It doesn't so much matter what they are, it's the movement that causes them to behave as they do. This is sometimes called just kinetic theory, and it may be abbreviated KMT for kinetic molecular theory, or just KT for kinetic theory. So you may see either of those on the AP exam. Let's look at the points of the kinetic molecular theory and some of the evidence for each of those. Alright, point number one says that gases in particular, because that's what we're moving into, consist of tiny particles called atoms or molecules. Historically, this is important because a lot of the evidence for the existence of atoms came from the behavior of gases. Of course, we're looking at it the other way around. We learned about atoms first, and now we're moving on to gases. So it may sound a little backwards to us, but that's because that's not the way that it actually happened. All right, the evidence for this is everything we know about atoms and molecules. The fact that equations, when they're balanced, describe real reactions and the quantities involved. The fact that we have the law of multiple proportions, the law of definite composition, all of these things. All right, second point is that these particles are in constant random motion. They're moving in a straight line until they run into each other, or they run into the container or something, then they bounce off, and that this movement is fast. Now, in the way of evidence, it seems like this would be a difficult point to come up with evidence for, but in fact, there's a lot of it, and it's low-tech kind of evidence. First of all, there's the fact that gases expand to fill the container. This makes sense if you think about the particles being in constant linear motion. One that is headed in a particular direction will keep going until it smacks into a container. So if you have a container that's like so, and you introduce a little cluster of atoms into one corner, they're all moving in different directions. If this one happens to be headed this way, it'll hit the container wall and bounce off and wind up over here. Maybe this one was headed off in this direction, and it will bounce off and wind up over here. And this one may go this way, but you can see how very quickly you would wind up with particles filling the entire container. And it's hard to imagine how gases might do that otherwise. All right, also, we are aware that gases have a volume that's usually about 1,000 times greater than the volume of the liquid. So if you have a 1 milliliter puddle of water and it evaporates, you'll have about 1,000 milliliters of water vapor. Again, this makes sense if you know that the gas is made of small particles that are bouncing off each other and just going crazy in all sorts of random directions. All right, furthermore, we know that gases have extremely low densities. Again, if these particles are moving rapidly and slamming around, there's going to be lots of room in between the particles. It's ultimately as much room as the container will allow. However, although they have very low density, they are compressible. There's plenty of space between those atoms, and so if we start moving this ceiling down on top of them, we can push some of the atoms into that empty space and compress them quite a lot. Hard to imagine how we could do that if there wasn't empty space available, and if there weren't atoms that were not occupying that space that could be moved into that space. All right, there's also the phenomenon of pressure. Pressure is a force that gases exert on their container. And if you imagine the gas as being a collection of particles, then you can see that when this atom comes over here and hits the container, it's pushing on the container. Not very much because atoms are pretty small, but there are billions of these atoms all doing it. And so they're each exerting a tiny force, an outward push on the walls of the container. That outward force on each square centimeter of container is what we call pressure. So when you put air in your car tires and you measure when you have enough pressure, you're adding atoms into your tire until they're exerting enough outward push on the walls to meet the manufacturer's suggestions. All right. Now, speaking of them bouncing off of each other and bouncing off the container walls, those collisions between atom and atom, or molecule and molecule, or atom and container wall, or whatever, are elastic. And so we need to pause for a minute and talk about elastic collisions and inelastic collisions. We have a lot of different forms of energy, right? Heat, light, sound, electricity, magnetism, kinetic energy, gravitational potential energy, chemical potential energy. And when the energy is exchanged from one to the other, we lose a little bit of heat, and the rest of it changes into the new form of energy. In an elastic collision, all the kinetic energy stays kinetic energy. None of it is converted into anything else. In an inelastic collision, some of the kinetic energy is changed into heat. For instance, when you drop a basketball onto the floor of the gym, it won't bounce back quite as high as the position you dropped it from. That's because some of its kinetic energy was converted into heat and sound. You hear it go thump. And so it doesn't have as much kinetic energy as it did. It can't go as high as it did. It will go maybe 80% as high as it was. That other 20% of its kinetic energy was converted into something else. Well, in gas molecules, they don't behave like that. Their collisions appear to be perfectly elastic. All the kinetic energy stays kinetic energy. In other words, as they slam into each other, they don't slow down. They don't lose energy. They just keep on going at this frantic pace and continue bouncing off the walls. All right, so collisions are elastic, which means that all of the kinetic energy, if it didn't, these atoms would gradually slow down and slow down and slow down, and your gas would wind up being a puddle on the bottom of the container. That would be very unfortunate in the case of something like the atmosphere. You know, after a few hours or a few days or even a few centuries, the atmosphere is now a puddle on the ground. That makes it kind of hard to breathe. How do we know that this is in fact true? Well, because gases don't settle out. They don't slow down and become puddles. One of those little things that we don't think of very often, but we should be very grateful for. All right. Another point of kinetic molecular theory is that these atoms and molecules are completely indifferent to each other. They neither attract nor repel each other. They have no influence on each other's motion at all. And that's an approximation. In reality, we know that all particles do attract each other, at least weakly, because all particles are going to be experiencing van der Waals forces, either dipole-dipole attractions or hydrogen bonds or London forces. All of these are attractions between independent atoms or independent molecules, and there is no escaping them. So this is at best an approximation. So to use kinetic molecular theory in its simplest form, we need to make up an imaginary gas that doesn't have van der Waals forces. And we call that imaginary gas an ideal gas. So the equations that we're going to be using are not going to be strictly true of real gases, but they'll come within that 5% that we regard as pretty tolerable. We will, when we get into the AP part of gas laws, find out how to correct for that, and you'll see that it's a lot of trouble. It's really better to take your 5% error and be happy with it. Alright, anything else I need to tell you about kinetic molecular theory? Ah, yes. One final point is that the Kelvin temperature is going to be directly proportional to the kinetic energy of those particles. Alright, and evidence for that is the phenomenon of condensation. As the temperature drops and the particles move more and more and more slowly, that gives these van der Waals forces that they're not supposed to have more time to grab hold of each other and pull, which eventually will bring them together into a liquid. But at the speeds that gas particles are moving, there's just not enough time for that kind of force to be effective. So the fact that gases condense is one point in favor of this. Also, at 0 kelvins, at absolute zero, then the translation stops. Those particles may still be rotating or they may be vibrating, but they're no longer getting up and moving from one place to another. Well, there it is. Kinetic molecular theory in a nutshell, with evidence in favor of each of its major points. And we will move on to how can we make use of this to actually predict the behavior of gases and be able to do some interesting work with gases. Talk to you next time.